We're going to start chapter 14. In chapter 14, we're going to look at our second major statistic that we'll be using for the IA.
Is it part of the chapter?
No. Sure. So what we're going to be looking at today is correlation. So I want to be real careful from here on out. I've caught a lot of you guys using the correlation word kind of willy-nilly. Correlation has a very specific statistical meaning. We shouldn't use correlation unless we're actually talking about like statistical correlation, which we haven't done yet. So you shouldn't have used that word at all in a mathematical sense up until this point. So we'll talk today about what that really means and how to actually measure correlation. But that'll be the other major statistic that you guys will be computing as part of your IA. So we'll do a chi-square test for independence, as well as checking for correlation between the two variables that you're measuring. Okay, so to start this discussion of correlation, we're going to start with just looking at a scatter plot or scatter diagram. So when we talk about correlation, it's really talking about something very specific. So we talk about correlation when we have bivariate data. That's data from two separate variables. So you're taking every individual in your sample, you're measuring two things from them, like height and weight, or political party affiliation and their opinion on some political issue, or gas mileage and horsepower, or whatever, right? Favorite color and gender. Correlation is the relationship between the two variables. So notice that we're being intentionally vague here when we say the relationship between the two variables, right? We don't specify the kind of relationship between the two variables. And it doesn't imply how strongly the two variables might be related. So you can have strong correlation, you can have weak correlation. In either case, those two things are correlated. It's just the degree of correlation that you're interested in. And by relationship, again, we're not being specific here. We're not saying what kind of relationship it actually is. Okay, so all we're talking about are how related these two things are together, but we're not actually defining what related means when we speak about correlation in general. Okay. So if we're talking about correlation, we really want to start by deciding which variable is independent, which is dependent. So the easiest way to think about this is the independent is like the cause, and the dependent is like the effect. So again, when I think independent, I think cause. When I think dependent, I think effect. Independent is X. Dependent is Y, going back to like Algebra 1 times. All right, so let's look at a couple of examples, and we'll decide whether which one of the variables, what the two variables are, and whether they're independent or dependent. So the size of someone's hand and their height. Which one is the independent, the cause, and which one would be the dependent, the effect? The size of the hand is the, which one? Dependent, sure. So the height is your independent variable. Typically, the taller the person, you know, like your body grows proportionally. So if you're taller, you expect your hands to be bigger as well, right? Everybody's okay with that? Sam's like, I don't know if that's the case. Do you not have big hands for being tall? Yeah. How about the second one? It says, if a company spends more on advertising, will the company sell more of its product? So what are the two variables here? Advertising budget and, yeah, like your revenue, right? Okay. Or units sold or whatever. Which one is the independent variable? Yeah, your advertising budget. You'd expect that if you're spending more on advertising, you should sell more stuff. At least that's the hope for advertising, right? That's good. Okay. One way to examine the relationship between, it's the projector. It's the fan and the projector. It's really annoying. One way to examine the relationship between two variables is to look at a scatter plot. So essentially, we take each individual and their response and turn that into an XY point, and we graph the points. So again, you're deciding which variable is the independent and dependent variable. Remember, the independent variable is your X and the dependent variable is your Y. We want to label and scale our axes. So, you know, it could be in, you know, dollars spent on advertising, and then units sold could be our X and Y labels. We'd want to have a scale on there. For advertising, since it's in dollars, maybe tens of thousands of dollars would be the unit. And number of units sold is maybe like, you know, in hundreds of thousands of units, depending on what you're selling. You know, if you're a company that sells like billions of items or billions of units of something, you know, like you're the toilet paper company or something, sell a lot of toilet paper. And then the last would be to plot the values. So no big deal here, right? We're just making a graph and plotting. So when we examine our scatter plot, we're essentially going to be looking for four things. So we're going to look for the direction, form, and strength of the relationship, and then any important outliers or divergences, departures from that overall pattern. So when we talk about direction, we're talking about the overall trend of the data. So you have two directions. You have positive or negative. So if the direction is positive, as you read the data from left to right, the data would be trending upward. If the direction is negative, as you read the data from left to right, the data is trending downward. Okay? We say negative and positive because it's like a slope, right? The form is you're describing the shape of the graph. So typically the shapes you would use are going to be the names of common functions. So a function might be, or the form might be linear or quadratic or exponential or something like this, right? Our common graph shapes from like Algebra 2 and pre-calculus. The strength is going to be how much the data resembles those curves. So the more the data looks like a finely drawn line, the stronger that relationship is, the more kind of spread out the data is, and it's like, oh, that's kind of the right shape, but it's a little like messier looking, the weaker that relationship would, or that strength would be. And then we know what outliers are, right? Something that diverges from the overall pattern. Okay, so that's kind of the idea here. So again, when we talk about direction, we talk about positive association or negative association, basically just whether it's trending up or trending down. Slope, basically, is all we're talking about here. So if we look at this example here, what would the direction be on this example? Negative, because it looks like kind of goes down as we move from left to right. Everybody agree? What would the form be for this? You might say linear, but if we look at this, maybe a better answer even would be, what kind of curve looks like that? Exponential, I think, is maybe the better one. Linear, probably not wrong. If you did the analysis, the shape probably comes out pretty strongly linear. I bet it's a little bit more exponential though. Because we can see there's an obvious curve to it. The strength of this, what do you guys think? So we'd either say weak, moderate, or strong. I would say it's more moderate to strong, in that neighborhood. Okay? Maybe it's like a wimpy strong or a strong moderate, but it's pretty clear the shape of this. It's now, the data is a little spread out. It's not like a tight line. And then last thing we'd look for, do you guys see any potential outliers?
4.6.
So like this guy and this guy, right, are probably the two potential outliers. And again, to describe those, you just describe them as an ordered pair, right? X comma Y. So here's our example. So we have our strength, our direction, and our form. And then we mentioned the two possible outliers. Everybody feel okay? Let's do it again. What's our direction here? Positive, agreed. The form? Linear, I agree. The strength? Moderate to strong, I would say. Again, you can definitely tell this is a line, right? Is it like the tightest line you've ever seen? No, but it's, like definitely you can tell the shape to it. Any potential outliers? Doesn't really look like it, right? So, blah, 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 positive association. And I guess this is about a football team or football teams where we're looking at the points per game they're scoring and the number of wins they're getting in a season. So we conclude that the more points you score, the more wins you get, right? Which is probably pretty typical. Again, we said a linear pattern for the form. The strength, we said moderate to strong, so I said fairly strong, whatever. No outliers. Everybody feels okay doing this? Now, we're not doing any calculation here. We're just kind of using our eyes and like describing what we see, right? Yeah, no big deal. So one thing that we'll want to be able to do with our scatter plot is be able to sketch a line of best fit. So that line is drawn so that it's as close to all of the data points as possible. And it's basically a representation of the correlation between the two variables. When you guys are sketching a mean line or a best fit line, you're going to start by plotting the mean point. So the mean point has coordinates average of the x's and average of the y's. And then your best fit line, you're going to just draw through that mean point as an approximation, right? So if I'm asking you to sketch this, what am I looking for? I'm looking for that it goes through the mean point and then it's not ridiculous, right? If like all of your data is above, your best fit line, that's not very good, right? You want about half your data above and about half your data below going through the mean line, unless you have like a cuckoo crazy outlier, and then it's a little bit harder to tell where it should go, but that's the idea. All right. I want to talk here a little bit about these two C words, causation and correlation. They are not the same thing. In fact, causation is extremely difficult to show. Correlation is much, much easier. So to give you an example between the two, I have this stapler, right? Sits here on my desk every single day. I've also never seen a bear in my classroom. I conclude that this stapler is causing like a field that just like keeps bears away. No. What have I done here? I've confused causation with correlation, right? Now, are the presence of bears in this stapler correlated?
No.
Absolutely. Very strongly. Every time the stapler's been here, have we ever seen a bear? Great correlation there. Very strongly correlated. Is the stapler actually causing the bears to stay away? No. What is actually causing the bears to stay away? Well, some confounding variable, right? Likely the biggest factor is the relative location, that there's really no bears in Oakland County to speak of outside of maybe the Detroit Zoo. Is that if you went and dropped me into like northern Alaska with the stapler, I'm guessing that it's not going to keep any bears away there. Everybody kind of see the idea here? We understand the difference, cause versus correlation. Everybody feels good? Don't be fooled by the two. All right. Blah, 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 blah. And this is just like, okay, here's another example. It says if 100% of students at NDP get accepted to colleges, could we say that attending NDP causes a student to get accepted to at least one college? Why or why not? Probably not, right? Why not? But is the going to this school causing that to happen?
Well, it was the year before us.
So here's what I would say. Could you have still been accepted to colleges if you went somewhere else?
Yeah.
Would the likelihood that you applied to college change if you went somewhere else? Maybe probably not. Most of us are like coming from expecting to go to college that attend a school like this. That's probably not going to change even if you went to Clarkston or Rochester or wherever else you decided to go, right? Now, the level of school you might be applying to might change depending on what high school you go to, or the expectation of where you're going to college might change based on this high school you're going to. But I would bet that the actual acceptance, like you applying and being accepted, isn't changing a whole lot, right? Just you have to apply to get into Notre Dame. Means you're a strong student already. You're exactly the kind of student that gets accepted into colleges already before you even started coming here. You know what I mean? It's correlated, not causing. You guys agree? Yeah. All right. That's 14.2 or 14.1. Ooh, that was so hard. It wasn't. Oh, this stupid thing. I want this thing to go die a death. All right. The next one is we're actually going to be looking at the two ways to calculate two different ways to calculate correlation. We'll actually talk about a third one, I think, later on. Bless you. All right. So the first measure of correlation that we're going to do is measuring the linear relationship between the two variables. I want to emphasize that, the linear relationship. So how much do these things look like a line? Okay. So to do that, we're going to use what's called the PMCC. That stands for Pearson Product Moment Correlation Coefficient. We represent that statistic with the lowercase letter r. How many of you guys remember r from Algebra 2 and Pre-Calculus? We did it. So R does two things. It measures the direction and the strength of the linear relationship. So R is always between -1 and +1. It's never bigger than 1 or smaller than -1. Positive values of R mean that it has a positive direction. Negative values mean that it has a negative direction. Values near R or near 0 indicate a very weak linear relationship. The further away from 0 you get, the stronger your linear relationship gets. until you get to exactly -1 or +1, which implies that you have a perfect linear relationship, meaning that the data that you plot, if you plotted that data, it would all lie on the exact same one line. None of it's going to be like offset a little bit. It is 100% a line. It is as linear can get. Is everybody okay with that? So we can calculate this R value as a number. To help us interpret that number into words, we can use the following guidelines. So R values between 0 and 0.25, we say is weak, or very weak. Between 0.25 and 5 is weak. 0.5 to 0.75, moderately strong. And 0.75 to 1, very strong. So that's going to be our kind of guideline to how we interpret the R value number into words. Like, what is this strength of the linear relationship now? Now, keep in mind, this is only a linear relationship, right? Two variables might have a really strong correlation to some other shape and not have a strong linear relationship. Everybody's okay with that? Okay. So let's look at a couple of pictures now. So to build a little intuition of what these different R values would look like as a scatter plot. Here's a scatter plot whose correlation is approximately 0. Notice that there doesn't seem to be any discernible pattern. There's no real trend to the data here. This one, the correlation is -0.3. Very little difference between these two, other than maybe you can see like a slight downward trend in your data. You guys see that? But it's subtle, right? This scatter plot is +0.5. Other than I can see like a slight positive trend, this doesn't seem to be any closer grouped together than this data does. Right? We see now how hard maybe picking out a correlation with just using our eyeballs is. It's nice to have a calculation to go along with it. Here is a -0.7. So there it looks much more like a line, right? It's a thick line, but it still looks pretty linear. This is a correlation of 0.9. This doesn't seem to be really that much thinner than this, but the correlation is quite a bit better. This one, everybody, I would hope that we would think that this is darn good. You know, -0.99, that's unmistakable as a line, right?
That's my God.
Does everybody feel okay here about just like trying to build up some intuition about what this looks like and how subtle the differences are between like 0 and 0.5? Like, doesn't seem like those are that different at first glance. All right, so let's look at some pictures and do this ourselves. So we're going to estimate the correlation and then give the direction, form, and strength. So if I look at this guy, what do we think the R value is approximately here? 0.8, I think, is a pretty good guess. That's what I had written down, was a 0.8. What's the direction? Positive. The form? Linear. And the strength we said is? Right, so we'd say in words, I think that's just strong. Yeah, very strong or pretty strong or whatever. Okay, next picture. What do we think the R value would be here? 0.1. I have 0.3 written down, but that's pretty close. No, like, you're not far. Like, that's good enough. What's the direction? It looks positive to me, right? Right? Negative would be doing this. It's definitely not doing that, right? So it's more positive than anything else. The form, I mean, it's linear-ish. It doesn't look like anything else, right? It's mostly a blob. And the strength, this would be weak or very weak, right? Let's look at this one. Yeah, I think so too. R0, so there's no correlation here. Means that there's no direction, there's no form, and there's nothing to say, right? Everybody agree that this is like just nothing going on here? Okay. How about this one? Positive or negative, though? I think it looks negative to me. Most of the data looks like it's going in this direction. But like a negative 0.3, I think is a great estimate. So the direction is negative. The form is linear. It doesn't look like anything else, right? And this is pretty darn weak, right? Yeah. Okay. So just some basic facts here about correlation. So if I switch the independent dependent variables, the correlation statistic, the PMCC, will not change. It's not dependent on independent or dependent variables. That has no effect on the number. If I change the unit, if I change my x's from being measured in feet to be measured in meters, won't affect anything. If I change it from so that's a multiplicative conversion, right? If I change it from Celsius to Kelvin, still no change. That's an additive conversion, right? Still doesn't make any difference. That PMCC statistic has no unit of measurement. It's not a percentage. It's not feet or inches or meters. It has no unit at all. We can only do this with quantitative data. So if you have what's your favorite color? Can't do anything. I can't do a PMCC with that, right? The PMCC doesn't describe curved relationships between the variables, no matter how strong. So if something is a awesome looking parabola, your PMCC is going to be lousy because there's not a linear correlation between the two variables, even if it's an awesome looking parabola or something. And correlation is not resistant. By that I mean that the R value is strongly affected by maybe just a few outliers. And the last is that this is not, the PMCC is just not a one-stop shop. It's not a complete summary of that two variable data. You may have a really awesome relationship, just not a linear one. Or even if your PMCC number comes back great, you may look at your scatter plot and go, yeah, I don't buy that for a minute. Looks like there's something else going on here. So let's talk about how we compute this value for R. Now, in general, the calculator is going to handle this for us, but the formula to do this is we're going to take 1 over the number of samples in our data set, and we'll take each x value, subtract it from the mean of the x's and divide it by the standard deviation of the x's, and then multiply that to the first y value minus the mean of the y's divided by the standard deviation of the y's. And we'll do that for every ordered pair in our data set and add them all up. So if I use a summation symbol, this is the formula. Now the calculator can do this for us, but we should be able to kind of set this up by hand. And we'll show you how to do this stepwise on your calculator and just in one shot on your calculator. Probably some of us remember how to get R from our calculator in one shot. So far, so good. Just a formula. All right. So let's take a look at an example. This is like the value of a car based on how many miles it's driven. So here I put the miles driven as the independent variable and the price as the dependent variable. If I look at, well, the R squared value, which is related to R, but we'll talk about what it means more. If I switch this then and put the miles on the y-axis and the price on the x-axis, notice that my equation for my best fit line has changed pretty dramatically, but that R squared value stays exactly the same, right? That R is independent of what variable is x and which variable is y. That's what I'm illustrating here. So take a look at these 4 scatter plots. These all represent a very different situation, right? You'd say all these 4 scatter plots have very different relationship between the 2 variables, right? Guess what? They all have the exact same R value. Again, what is this reinforcing to you? That R is not the end-all, be-all of what relationship is going on here, right? Of these, which ones would you think that the R is telling a reasonable picture for? A. That's the one that's giving you the best, R is giving you the best representation of, right? What's the matter with B? Why isn't R telling us the best story?
It's not linear.
Yeah, this looks like it'd be better described as like a quadratic relationship, right? Everybody buy that? Looks like a parabola. And that thing, and I would guess that it's really strongly correlated with a quadratic relationship. What about C? Yeah, that looks like an awesome linear relationship, way better than 0.8. It's just that one stupid outlier that's screwing everything up. What about the last one?
Really messed up.
Yeah, I'd expect a really lousy R value if not for this one mega outlier here, right? But somehow that mega outlier is like tricking the calculation into thinking that like, oh yeah, there's a nice linear relationship here. It's like there is nothing going on here, guys. This is a bunch of gobbledygook. Okay? So again, the takeaway from this slide is that the R value alone is not enough to say that, oh, look at these great relationship between these 2 variables. It's only going to reinforce kind of what you see. And even in practice, as a mathematician or a statistician where you're doing like some modeling in the real world, even if you build like a linear model that has a really great R value, you need to ask yourself, does it even make sense to have a linear relationship between these 2 variables? A lot of mistakes in prediction get made assuming a linear relationship when that's really kind of inappropriate. A nice example of that is a lot of your climate modeling is kind of assuming linear relationships when maybe that's not our best model for temperature. And even better, so they all have the same R value, and if I drew in the best fit line, they all have the same best fit line, even better. Look at that. These are definitely not the same data sets though, right? Yeah. Okay. All right. So here's an example. So we have some scatter plot, right? We've drawn in a best fit line. Looks like there's 2 potential outliers here. Everybody agree? So these outliers are going to have some effect on the R value. Well, this slide is going to illustrate as to you the kind of outlier that has more effect than another. So if we look at this, if I calculate the R value with everybody in it, I get a negative 0.64. If I remove this child up here, child 19, this is a data set of like children's Gessel score, which I think is like an IQ test for children. and then the age in which they said their first words. If I throw this guy out, my R value improves a little bit. Everybody see that? If I take child 18 and I throw them out, my R value gets worse. Right? Everybody sees this? So sometimes the removal of an outlier can improve your R value score, and sometimes it can make it worse. If I look at the 2, child 19 is an outlier in X or Y. It's in the Y, right? There's lots of other data with the same X coordinate or similar X coordinate, but you're all kind of by yourself in the Y direction. The removal of this kind of an outlier typically will improve your score. Child 18 is an outlier in, well, both X and Y. Particularly the X direction, though. These guys are your bad boys. Yeah, the X direction is the one that really has a large impact on your R value. So like an outlier in the X direction can make something that doesn't really have much of a linear relationship look like it's a lot better than it actually is. So that's our takeaway from this slide. What's up? Oh, you whispered something. I didn't know if you were trying to... Hey, you had a question there, or you're just talking to yourself?
No, it's just 40 months is a while.
For a first word, yeah. Yeah. That was you? Okay, cool. So we say stuff like child 18 are influential. So these are points that are like have a really strong impact on our R value. Typically, those are going to be outliers in the X direction. So just again, this is a little piece of vocab about just what we talked about. A second correlation calculation is called the Spearman rank correlation coefficient. The first one was Pearson's product moment correlation coefficient. The difference between the two, Pearson is a linear relationship. Spearman will describe the strength of any positive negative relationship. So if your function is generally increasing or decreasing, Spearman's going to cover that even if it's a curve or not. Okay? So the Spearman rank correlation coefficient typically we abbreviate as an R sub S, or we use the Greek letter rho. Just like the Pearson's, the Spearman statistic is always between -1 and 1. Positive values describe positive direction. Negative values describe a negative directions. Values near 0 indicate a very weak relationship. The strength increases as we move away from 0, and the values at -1 and +1 exactly occur only if you have a perfect rank order relationship. By that I mean that every single value is like basically on a line. We'll talk about like what the values are we're talking about, because we don't use the data directly to do a Pearson coefficient or Pearson calculation. I'm sorry, we don't use the data directly to do a Spearman calculation. Indirectly we use it. We'll show you in a minute. All right, so let's look at an example here. So mobile phones often lose their resale value quickly. The following data is collected for one particular model. So the age of the phone and the value as a percentage change in value. So like after 2 months, it's worth 29% less than what you paid for it, all the way to 24 months where it's worth 87% less than what you paid for it. To do a Spearman calculation, oh, sorry. Let's plot the data first. So if I look at this data, this looks like what kind of form? Looks kind of exponential to me, right? It's still linear a little bit, but I bet an exponential would be a better fit for this than a linear. If I did the Pearson calculation, this comes out to be negative 0.874, so still pretty strongly linear. But I know that it's not, like if I did my linear calculation, I'm pretty positive if I pick a big enough x, it's going to give me a value of less than a negative 100, which I can't have less than negative 100% change in my cell phone, right? The value of your cell phone can't be like negative value, right? It can't be worth less than what you paid for, less than zero. You know what I mean? So that makes me think that maybe although a linear relationship fits pretty well for what I have, probably not a great fit overall. However, if I just want to look at the like the consistency of the positive negative relationship, that the Spearman can do really well. So to do a Spearman calculation, the first thing I want to do is change our data into rank order data. So all I'm going to do is number the data for each column in order from highest to lowest. So the highest value in the X is 24, so that would turn into 1, and then 22 would be 2, 3, 4, 5, 6, etc. And in the Y column, my biggest value is 0, so that would be my 1, and then I have 2, 3, 4, all the way down. So if I do that, this would be my new rank data. Is everybody okay with what I did there? Nora? Sure. Okay. When I do that, I can now find the correlation using the same formula as the Pearson. I'm just going to be using the rank data instead of the raw data, but it's the same formula as a Pearson. So if I plot this, this is my scatter plot. Ooh, boy, that looks pretty linear now, right? And as a result, the Spearman gives me awesome relationship, which tells me that overall there's a really strong negative trend. So the longer you own the phone, the less it's worth. And that is a right strong relationship. Everybody feels okay with what we did there? Okay. What if I had instead ranked them in the reverse orders? What if I went, instead of big to small, if I went small to big? So here I've gone and just flipped them. If I look at the graph, what do you notice? Nothing changed, right? And the Spearman value is exactly the same. So as long as you're doing your ranking consistently, doesn't really matter if you go small to big or big to small. I always go big to small, though. All right. What happens if I have ties within my data set? So let's say we have this data set. If I look at the X's, ooh, I have 2 3.5s, and then I have 3 6.5s. Oh no! All right, so what would I do here? So let's start by doing our ranking. So if I look at the X's, 7 is the biggest value, so that's my 1. 6.5 is my second biggest value, so these 3, I'll get 2s. Everybody's okay? My next biggest value is 6, but that's actually the 5th value that I've ranked now, right? So I go from 2 to 5 for 6 because it's the 5th number I've ranked. And then 5.5 would be 6, 5 would be 7, 4.5 would be 8, 4 would be 9, And then 3.5 is our 10th value. So those would both be 10s. Everybody's okay with that? So I've just ordered my data. So this works very much if you guys are, did your track and field kids. There's like a tie in the high jump for first place. Those two are both awarded first place, and then there's no second place. They just award third place, right? Same idea. Everybody's okay with that? However, this is not my rank order data. This is just my ordered data. Because I have ties, my ordered data is not the same as the rank order. Oh no. So the difference is going to be the values for 10 and 2. So much like if you're scoring at a track and field meet, if you have a tie for first place in the high jump, both first placers aren't given first place points. They're given the average of the first and second place points. Because you can't award more points for an event than there are in the event, right? If you gave both of them first place points, you've awarded more points for high jump than any other event, which is not what you want to do. So to fix this, I have to give those values, the second number on my order, I have to give them the rank of second place, plus third place, plus fourth place, averaged. So that's a 3. For these guys, Kevin and Steve, that's 10th place and 11th place. So those guys should get this rank of 10.5. So this is the data that I'm going to calculate my my spearman with. Alyssa.
Rank the hours and grades.
Yes. Okay. Yeah, the out or the grade I didn't have to do anything to because there's no repeats. There are no ties. So it was just like the rank order, or the order is the rank order. The only time you have to worry about it is when there's ties. So the ties just get the average of the places. Okay? All right, so we have this. If I do my spearman, I get 0.814. If I didn't give these ranks, if I just use the orders, I get a different number. So you absolutely have to make sure you're ranking these correctly. We'll practice this. It'll be in the homework and stuff. Once you do it a couple of times, you're like, yeah, I got the hang of it. It's no big deal. But like, it's weird the first time you do it. Grace.
How'd you get 2 plus 3 plus 4?
Okay. So Cindy is first, right?
Yeah.
And then places second, third, and fourth are occupied by the rank 2. So that's where the 2, 3, 4 comes from. And then 5th place is here, 6th place, 7th place, 8th place, 9th place, and then 10th and 11th is a tie, so they'll be the average of 10th and 11th, right? 2nd, 3rd, and 4th place is a tie, so it's the average of 2nd, 3rd, and 4th place for the Anton, Lucas, and Julie. Does that feel okay? All right, so a few things. Let's compare and contrast these two statistics now, the Pearson and the Spearman. Yeah, bless you. So if I have this graph, we notice there's a big outlier here, right? So the Pearson formula gives me a 0.75. Does that seem real to you? What should the direction for this data set be? Looks negative to me. What's happening is this crazy outlier out here is dragging the calculation into the positive direction. It's like, oh, look, here's my positive relationship. Doesn't seem very reasonable, right? The outlier's fooling the Pearson statistic. If I do the same thing with the Spearman, though, I'm still getting a negative value. So it's here the outlier is not affecting the Spearman as strongly as the Pearson. So that's takeaway number one. The Spearman is going to be less affected by outliers than Pearson's. Everybody okay with that? That's the takeaway from this slide. So a little piece of vocab here that applies to Spearman. So when we describe a function, we can talk about monotonicity, or whether the function is monatomic or not. So monatomic, there's two types. There's monotomically increasing and monotomically decreasing. So if you're monotomically increasing, the function is growing or staying the same. So it's either increasing or level for the entirety of the function. So here we're increasing or staying the same, increasing or staying the same, increasing or staying the same. These are all examples of monotomically increasing functions. If the function is decreasing or staying the same, decreasing or staying the same, decreasing or staying the same, those are examples of monotomically decreasing. These types of functions are excellent candidates for a Spearman calculation. Spearman does really, really well on functions that are monatomic, as opposed to the Pearson, which wouldn't give you that same kind of, wouldn't observe that relationship in the same way, right? I mean, this one it would. Pearson have no problems here and here saying, yeah, that's rock solid dynamite. But this one, or this one, I don't know what the Pearson isn't going to give you as good of a value as the Spearman would. Now, if you're not monatomic, so you're something that like goes up and down, here the Spearman will not do as well. And the Pearson could do good, it could not do good, right? It depends on how much kind of up and down you're getting. Right, I'd expect the Pearson to do okay on this one. Pretty bad probably here. Yeah, not great here either, but the Spearman's going to be junk on all these. Do you feel okay? So again, it's just talking about, like, if I look at my scatter plot, can I tell which correlation coefficient I should use to give myself the best description of the relationship going on? That's what we're talking about right now. Grace.
So when there's an outlier, you're saying we should use Spearman?
Yes, typically yes, especially if it's a very large outlier. If it's not so big, maybe it matters a little bit less, but if it's a big one, definitely. Okay. Let's do some of our in-class examples. We still have one more section here, but won't get to that today. All right. So for the following situations, identify which is the independent variable, which is the dependent. Comment on whether you believe the variables will be strongly or weakly correlated and why. First up, the ACT score of a student, the amount of sleep per night the student gets on average. What is our independent and dependent variables here?
Dependent is the amount of sleep, and independent would be the ACT score.
Perfect, yes. Independent sleep, dependent ACT score. What do we think the level of correlation here is? Strong, weak, moderate? You guys are crazy. It should be weak. What's your strongest indicator of ACT performance? How smart you are. Not even studying time. It's legit just how smart you are, right? Not if you are a stone cold genius and you don't sleep before the ACT, how are you going to do? Very well. If you are like mentally handicapped and you sleep the entire day before the ACT, how are you going to do? Not great, right? Sleep, not your biggest indicator, not strongly correlated. You guys agree? I would say that weak would be my answer here. There's a lot of stuff that matters a whole lot more than the amount of sleep you're getting. Intelligence, studying, conscientiousness, like all matter a whole lot more. Next one, hours spent exercising per week and the number of years you live. Which one is there, independent and dependent? Exercise is independent, lifespan would be dependent. Correct. Level of correlation, weak, moderate, strong. I'd say probably moderate to strong even, right? Like, if you have excellent exercise habits, that's going to take care of a lot of your diseases that kill you early. Now, you could still have an accident, right, and die early. That happens. Or could be the victim of some terrible violence. And exercising doesn't help prevent those things. But if you're exercising regularly, very likely you won't have diabetes. You probably won't have heart disease. Like those are things that are your big killers in your 50s and 60s. If you can get past that, you've made it into the last quartile of lifespan. You're doing pretty good. All right, part C. The distance you live from a body of water and the amount of snow you receive in your backyard every year. Independent, dependent. Great. Strong, weak, moderate. You guys are fooled by lake effect in Michigan. This is weak. Think about people who live in Hawaii or on the California coast, right? Like, what's your much better predictor of the amount of snow you're going to have? Your latitude, right? Your relative latitude, or maybe even elevation, the combination of the two. Much bigger predictors of snowfall than presence of water. You could have a pond in your backyard. Is that going to make a difference? Even if you live somewhere north? Probably not, So this is me trying to fool you with your Michigan biases. And I did it. Ha ha! All right. We got 3 scatter plots. We want direction, form, and strength for part A. Direction. Negative. Form. Linear. Strength.
Moderate.
Yeah, I'd say moderate. B.
Negative.
Olivia. None. This doesn't look like there's any correlation here at all. If it's a none, that's it, right? C. Positive. Linear. Strong, or very strong even, I'd say. That's darn tootin' the line, right? Nobody's confused on that one. All right, for the following set of data, plot a scatter diagram and draw a sketch of the best fit line. Make sure you find and include the mean point. All right, so I'm just going to kind of do this on my calculator here real quick. So here's the data set. I just typed this into my calculator. Everybody's okay with that? I also calculated the mean and put that in as a separate set. So what I'm going to do, is I'm going to turn on plot 1, and I'm going to graph L1 and L2. This first option is scatter, and I'm going to use the block. Then I'll go to plot 2. I'm going to turn that on. I'm going to do a scatter. I'm going to plot L3 and L4, and I'm going to use a plus sign there. That's going to be my mean point. Oops. So if I do zoom stat, there's my scatter plot. Here's my mean point. If I draw a best fit line, it would kind of go like, I want to go through the mean point, would probably look kind of like that. So I'm just kind of sketching it in. Everybody okay? If I actually calculated the best fit line, I did this aside. You don't know how to do this yet. It's not expected you know how to do this. We just be eyeballing it at this stage. But that's what it would look like. The thing I'd be checking for is, does your best fit line go through the mean point? And do you have about the same amount of data above and below your best fit line?
How do you see the mean point?
I just took the average of the x's and the average of the y's and plotted that. No big deal, right? That's it for 14.1. In 14.2, it says, here we have some students' sprint times and long jump distances. Wants us to make a scatter plot for that. And then describe the independent dependent variables. What are the independent dependent variable here? You got sprint times and long jump distances. I think one is more obvious than the other. Yeah, the faster you are, typically the further you're going to jump. In fact, in track and field, most of the field events boil down to the fastest person in the field event is usually the best person in it. Even things like the shot put, as odd as that seems. All right, so if I wanted to go and graph this, so if I make my scatter plot L5 and then L6, and then I'll switch over and turn off plot 2 because I don't need that guy right now. And then I'm going to do zoom stat. Whenever I'm graphing a scatter plot, just picking zoom stat is your best option. So it just like gives you a window that you can see everything on. It's wonderful. Everybody cool? All right, what do we see here as far as your strength, direction, form? Negative. Form. Strength. I'd say moderate to strong. Yeah, this is probably strong. Not very strong, but strong. It says that the scatter plot has the value of negative 0.838. That's pretty good. Interpret this value in the context of the data. Okay, so this is talking about sprint and long jump times. What is this saying? That the smaller your sprint time, the bigger your long jump should be, right? That's going to be the negative slope. So little x's should go with big y's. Everybody agree? If it was positive r, it would be big x's go with big y's. So slow sprinters jump far. Probably doesn't make a lot of sense. Everybody's okay? Based on your scatter plot, what effect does the person that ran 7.25 seconds have on the correlation? So let's look here. That's this point right here. So our slowest runner still jumped pretty far, right? What do we think is going on there? If we got rid of him, what do you think is going to happen? I would expect the correlation to get better, right? Let's just show you real quick. So let's go down. I'm going to delete out that last fella there. If I do that, the correlation bumps up to negative 8.68. So improves a little bit. Not a ton, right? Because it doesn't look like he's much of an outlier, but gives us a little bit of improvement there. So far, so good. And again, I'll show you guys how to do this stuff on your calculator eventually. We're just kind of talking in general right now. All right, we got the same data. It wants us to calculate the value of R using the formula below, show an appropriate amount of work. So, what is my N? $12. My first X is 5.41. I don't know my mean yet. I'll calculate that in a second. My first Y is 171. I don't know my Y mean or my Y standard deviation yet. Everybody okay, kind of my setup here? All right, to get those values from my calculator, well, I have to remember I just took out that last data point, so I'm going to go put him back. Stupid slow jumper. All right. Now I'm going to get the mean and standard deviation for the x's and the y's. To do that, I'm going to go stat, calc. I'm going to pick two variable statistics using L5 and L6, which is where I put my data. So my x mean is 6.34. My SX is 0.686. If I scroll down, my Y mean is 124, I should say 125. And my standard deviation is 37.4. And I know this will come out to be like negative 0.838. Everybody okay there? Or if I wanted to do this with a list, so I'll make a new category here, call it A. In A, I'm going to do L5 minus vars statistics x mean divided by vars statistics standard deviation for x. Populate that guy. Make a new list. Oops. You stupid thing. Make a new list. In that list, I'm going to do L6 minus vars statistics, my y mean, divided by vars statistics, my standard deviation for y. So that's those. And then make another one. In this one, we're going to do list A times list B. Second list A times second list B. Enter. And then I'm going to sum up everything in this list and multiply it by 1 over n. So I'll do vars, stat, calc, one variable stat on list C. And I want that sigma x number there. So I'll do 1 over 12 times vars stat, and then sigma x. And there's with the same negative 0.838. We'll do this again in practice, but that's the idea. Okay. We'll do this in the activity and stuff. We did this already. Now it wants us to do a Spearman, but we have only 3 minutes left, so I'm just going to stop here. We'll finish this up next time. We still got a lot of stuff to do in this one.